ท่านผู้มีเกียรติทุกท่านนะครับวันนี้เป็นวันดีวันหนึ่งนะครับผมที่ทุกท่านได้มาร่วมสัมมนากันในวันนี้นะครับผมในหัวข้อเรื่อง Isokinetic Sampling and Application by Apex Instruments from USA นะครับซึ่งเป็นหัวข้อที่น่าสนใจมากที่สุดในด้านเครื่องมืองานตรวจวัดคุณภาพสิ่งแวดล้อมนะครับในปัจจุบันโดยทางผู้จัดนะครับบริษัท NEEDISS Supply Instrument จำกัดและผู้ผลิต Apex Instruments เชื่อว่าท่านจะได้รับความรู้และทฤษฎีต่างๆเพิ่มมากยิ่งขึ้นนะครับไปกับงานสัมมนาในครั้งนี้ก่อนอื่นใครขอเรียนเชิญตัวแทนจากบริษัท NEEDISS Supply Instrument จำกัดผู้จัดงานสัมมนาคือคุณนวรัตน์มิตรจิตโปรเจกต์แมเนเจอร์ได้ขึ้นมากล่าวเปิดงานและกล่าวรายงานวัตถุประสงค์ของการจัดงานในวันนี้ให้แก่ท่านผู้เข้าร่วมสัมมนาทุกท่านได้ทราบความเป็นมาพอเป็นสังเขปด้วยนะครับขอเรียนเชิญครับ
สวัสดีครับท่านผู้ร่วมสัมมนาทุกท่านนะครับผมนวรัตน์มิตรจิตนะครับในนามของบริษัท NEEDISS Supply Instrument จำกัดนะครับก่อนอื่นเราต้องขอเรียนให้ทราบว่าทางเราเนี่ยพยายามที่จะทำเป็นพันธมิตรทางด้านสิ่งแวดล้อมเพื่อที่จะให้พวกเราเนี่ยนำเรื่องพวกนี้ไปใช้ร่วมกันนะครับไม่ได้มองว่าทางบริษัทของเราเนี่ยเป็นในด้านของคู่แข่งทางการค้าหรืออะไรก็ตามเรามีเป้าหมายในการที่จะให้บริการแล้วก็ในเรื่องของการที่ต่อไปเนี่ยเราจะมีแนวโน้มที่จะเป็นในเรื่องของ Training Center อะไรต่างๆนะครับในวันนี้ทางบริษัท NEEDISS ได้เป็นตัวแทนจำหน่ายอย่างเป็นทางการกับของเครื่องมือของ Apex นะครับก็คือเราได้ร่วมมืออย่างเป็นทางการในการจัดจำหน่ายก็ได้เชิญทางทีมงานอะไรต่างๆเนี่ยเข้ามาในเรื่องของการเกี่ยวกับในเรื่องของการจัดการใช้เครื่องมือเทคนิคการใช้เครื่องมือหรือพวกแอปพลิเคชันอะไรต่างๆนะครับก็หวังว่าในการสัมมนาครั้งนี้พันธมิตรทางสิ่งแวดล้อมทั้ง24หน่วยงานที่เข้ามาร่วมงานในวันนี้จะได้รับความรู้แล้วก็นำไปใช้ประโยชน์แล้วก็ได้ทำงานทางด้านสิ่งแวดล้อมร่วมกันนะครับขอต้อนรับอย่างเป็นทางการอีกครั้งหนึ่งครับ
นะครับผมลำดับต่อไปผมขออนุญาตแจ้ง agenda คร่าวๆให้ฟังนะครับผมโดยช่วงเช้าเราจะมีกันเรื่องทั้งหมด2 topic นะครับผมโดย topic แรกนะครับจะเป็น topic เรื่อง Revolution for Console of Isokinetic Sampling นะครับรุ่น XD-502 ครับผมแล้วก็ช่วงที่2จะเป็น topic เรื่อง Key of Equipment for PM 2.5 and PM 10 Sampling by Isokinetic Sampling นะครับจากนั้นเราจะพักเบรกแล้วก็ช่วงบ่ายจะต่ออีก2 topic โดย topic ที่3นะครับจะเป็น Key of US EPA PS 11 นะครับ Untitled with Isokinetic Sampling ครับแล้ว topic สุดท้ายจะเป็น Mercury Sampling by US EPA Method 30B นะครับแล้วก็ Advantage Agent with Isokinetic ครับผมลำดับต่อไปนะครับขอเรียนเชิญผู้ดำเนินรายการสัมมนาในวันนี้นะครับมิสเตอร์มิกซ์ซาโบดำเนินรายการต่อไปครับขอบคุณมากครับ
That you may have, but today I'll share with you some basics on isokinetic sampling, some of the methods from the US EPA, and then we'll look at the equipment that we can supply to do this sampling. Apex has been in business over 30 years, 32 years. We are based only 15 minutes from the US EPA Air Quality in North Carolina Division. And we work very closely with them in developing new methods, new equipment, improved techniques, things like this. And we help governments and customers in over about 80 countries around the world. And we're seeing some new improvements in places like Africa, some new regulation, new implementation of isokinetic sampling, which is encouraging. It's good to see that new markets in certain places of the world are developing for human health reasons. I would say with my experience here in Thailand that Thailand is one of the better industries in the world, very well educated, been doing sampling for a long time. So I enjoy coming here and sharing my experience with you. So we can get started. So for the first session this morning, and I'll do my best to speak as clear and slow in English as possible, on the original Method 5 theories and practices. And you must have a basic understanding of Method 1, 2, 3, 4, and 5 to be able to do more sampling, maybe Method 23 or 26A or 29, things like this. So we'll review those methods, and then we'll take a look at the new console that we have in the back here, the 502, which is a small, light, compact version of our original manual sampling equipment that we have developed over many years with feedback from our customers all over the world, looking for new technology, new improvement on the equipment. So first of all, let's talk about what isokinetic sampling is. And to break down the word itself, ISO is the uniform or same or equal to, and then kinetic is pertaining to the motion, or in our case, the flow. So isokinetic sampling is basically matching our flow or suction with the instrument to the flow of the stack gas. And why do we do isokinetic sampling? It's to provide a basis representative sample of the particulate matter emitted from the source. So when we withdraw the gas at the same speed that it is flowing through the stack, we can then determine the total emission rate coming from that source. As a side note, it is only particulates or particle-bound parameters that need to be sampled isokinetically. Gaseous forms of parameters can be sampled at a constant rate, and we can make our calculations from there. So the reason that we do this, obviously, is to determine the emissions coming from a particular industry or a particular region or a particular country that hopefully government officials can use this information to determine regulation or improvements for the public health and what should be done. That is from a regulatory side, okay? Also, there are benefits for the facility itself to do isokinetic testing, maybe for the optimizing their processes. At the end of the day, when you have a lot of particulate, maybe a lot of gases exiting from a stack, at the end of the day, that is product. That is something in the process that they're losing to the atmosphere. So if we can reduce this and improve our emission rate by lowering it, we should have better efficiency within the facility, whether it be the heat for the boiler or different processes along the cycle, from the raw input to the exit of the stack. Obviously, we talked about the regulatory requirements and improving data for the health risk and what the government will decide should be improvements to help the overall population. So when we talk about US of dust that is exiting the chimney or the stack into the surrounding atmosphere and exiting from facilities, is its cause to human health. So total dust, or method 5, is going to look at all dust and all sizes. Do we have some people here that need to come in? Yeah? So it's going to account for all sizes of dust. It doesn't matter what it is, big, small, whatever. And then the US EPA, over the last 20 or 30 years, through scientific research, has discovered that the smaller the particle size, the deeper into the human lungs that particulate enters, and it enters into the bloodstream and has more severe health effects than the larger size PM. So typically the rule is, you can see here, PM10, the size of the particle, is filtered out by the respiratory system, the nose and things like that. Between PM10 and 2.5 are caught in the lungs, in the capillaries of the lungs. Then PM 2.5 goes deeper into the human lungs, and now the new research in the United States is looking at PM1 and how that enters into the bloodstream and the health effects for that. So today also, during our presentations here, we're going to look at our PM cyclone for determining particle size, PM10, PM 2.5, and then maybe PM1. Now, I was talking with some people yesterday at the hotel, some local people, and they were saying that in the last maybe 6 months or 1 year here in Thailand, PM 2.5 has become a very big issue with the general public, which is really good. People are getting educated, and they're asking the questions, and they showed me the public website where you can visit and see the ambient stations around Bangkok that are showing the PM 2.5 levels. So this helps generate pressure on industry and on the government to improve sampling regulation, to do more of it, to determine how we can lower that PM 2.5 number. So there are several sources where that may come from, maybe vehicles, maybe the burning of farmland when crops are changed and things like this. And obviously here in our industry, we're looking at stationary sources, chimneys, factories, things like this, that contribute to that PM 2.5 factor. So we can talk about that a little bit later on. So isokinetic sampling, and I won't go into the mathematics too much today. If you have any questions on the calculations or anything, I'll be happy to answer it. But let's just make sure we understand the theory and the topic today and what needs to be done for an accurate sample. The key is accuracy here, because if we're not taking an accurate sample, the data is meaningless, and then maybe we're making decisions on incorrect information, and we're not improving the situation as we think we would like to. So we're looking here at 100% isokinetic sampling. So this represents our nozzle here on the end of the probe. You can see that over here on our system, match how much gas we suck into the nozzle with our pump. So we're going to draw our vacuum, and how much gas we pull into the nozzle here is going to equal how fast the gas is flowing past that nozzle, okay? And we're going to use several parameters to make sure this is accurate. Our pitot here, reading how fast the gas is coming towards this. So we need to do all of our calculations. In the US EPA regulations, it says a valid test is, and our isokinetic rate will be our delta H, which is the gas leaving the back of our gas meter. That is going to equal our K factor here, and the K factor is an equation about this long, taking into account our nozzle size and our humidity and pressure and things like this. And our delta P reading, which is the reading we take from our pitot tip on the front. Okay? That's how we're going to determine our isokinetics. So we're looking for, again, this is our reading the delta P from the pitot tube, and then we adjust our sampling rate accordingly based on stack conditions and the K factor number that we have previously calculated will get us our isokinetic sampling rate to be spot on. Again, this is the K factor equation with all of these parameters here that we're taking into account to calculate our isokinetic rate to be as close to 100% as possible. So all of this must be performed before we even start pulling or drawing the sample with our system. So there's a lot involved in making sure that the accuracy of our test is correct. So let's take a look now what happens if we are not isokinetic, if we are not 100%. So if we are more than isokinetic, we're sucking in more gas faster than it is flowing through the stack. What tends to happen is, you'll see here, these represent the particles. They are typically pushed away from the nozzle as we're sucking harder and faster than we should be against the flow of the gas. So if we're over isokinetic, we're pushing the dust around the nozzle like this. So now we're getting a smaller amount of dust in the nozzle than is actually in the gas. So now we're biasing our results on the low side. We're now going to report that there's less dust in the stack than there actually is. On the reverse of that, if we're 200% lower, we're higher in our isokinetic, we're going to have a lower concentration of our stack, because what's going to happen is we're going to push some of the larger particles away and only collect smaller particles. It's not going to be a representation of all of the dust across the stack. So this shows the reasons why isokinetic sampling is key in getting an accurate representation of what is coming out of that stack there. So let's take a look at the methods, and then we'll look at them one by one really quickly to see. So first is our method 1, which is going to determine our sample and velocity traverses from a stationary source. It's going to help determine where on the stack we sample, and it's going to help determine how many points across the stack that we can sample. Now, I travel to a lot of places around the world, and the facilities compared to some of the factories in Europe or US or whatever are much more challenging, let's say, in terms of access to the stack. Sometimes there's only one port that we can test, where at minimum we should be having 2. Maybe the location of the port is not ideal. So in practical senses, I very much understand that sometimes there's unique challenges when you go into the field and actually do the testing in real life. But at least if we know the ideal situation, the best way to do our testing, if we have to make changes to that philosophy, to that testing parameter, we will know and we'll be able to share that with the customer or the government or whoever is looking at the results. We can share the changes that we've made with them so we can take into account maybe variations in the results that may not be quite as accurate if it was a perfect situation. The gas is actually moving and our volumetric flow rate, and that'll help us pick and determine a nozzle size that will be the best for us to draw the sample through. Third is we're looking at our molecular weight. Again, all of these calculations, and the reason we do this is it's information that we need for our K factor calculation to again determine our isokinetic sampling rate from our meter box. Method 4 is to determining our moisture content in the gas in the stack. And then finally, once we've done all that, we'll actually start testing and drawing a sample and pulling gas from the stack. So quickly, method 1, and I'm sorry if you guys are familiar with this. I'm not sure who is not familiar in the room, but I think a good review is always nice, hopefully. So we're going to select our appropriate sampling location, determine the required numbers of traverse points across that stack, and then calculate the location of the sampling points within the stack, and then we're going to mark them appropriately on our probe so it makes us easy to sample while we're going through the process. So some of the challenges for method 1 is cyclonic or swirling gas flow. So if we've got a chimney and the gas is going like this, or it's going like this and bouncing back off the walls, it's going to be very difficult to get isokinetic sampling because the flow rate on this side might be very low and the flow rate over here might be very, very high, okay? So it does make it difficult because maybe the instrument cannot suck hard enough on the high flow side, determining a nozzle that will work for all parameters in the stack. So that is a challenge, can be. The other is small 30 centimeter stacks that are quite small. Doing a cross-section, a traverse, is very difficult to do. Just that it's such a small surface area to move the probe just a couple of centimeters each time is not really representative of the stack and what we're looking for. So in that case, you would actually use method 1A, which has variations approved by the EPA for these small kinds of stacks. And I'm not sure the situation here in Thailand. Are they typically big, small, somewhere in the middle, a bit of everything? I don't know. Yeah, but it can be a challenge. So the sample location, and we can talk about this here in a minute, is you need time after the last disturbance, so maybe a turn in the pipework or a fan, to allow the gas to change and get uniform across the stack. Okay, just after a turn, the gas is going to come out and it's going to bounce from each side. So you need time for it to settle down and come up nice and smoothly, again, to help our isokinetic sampling rate be as close to 100% as possible. So determining where we should be sampling on that stack, we should be at least 8 diameters from the last turn. So if we have a 1 meter stack in width, we should be at least 8 meters above the last disturbance. A turn, a fan, something like this. We should also be at least 2 stack diameters, so a 1 meter stack. We should be 2 meters down from the exit point of our stack. And the reason for this, obviously, the upstream, the 8 meters, is allowing the gas the flow to get as uniform as possible on the stack. And then coming 2 diameters down from the top, we are ensuring that we're not sucking ambient gas from outside the stack that may be coming in from the top of the stack down into the gas. We don't want any ambient gas. We only want the gases coming from the factory or the facility up the piping. So, and then this is a little cheat for determining how many traverse points you have, sampling points you have for how big the stack is. So really you're going to be choosing somewhere between 8 and 12 individual points that we're going to sample to get a representation of how much dust is coming out of that stack. So you can see here, this is showing you here, this is the turn in our stacked or our duct, so we need to be 8 widths up the stack from there and at least 2 down here from the top of our stack. Now, again, sometimes it's not our choice where we can sample. We have to just use what the facility provides us. But if you have any customers that are asking you, where do you want me to put the portholes? Where do you want me to put the sampling location? You can help them determine the correct place for this by using method 1. So in the future, when you return to that site and do more testing, that you know that you're doing the best possible job you can determining where you should be sampling. So let's take a look at our areas. So in a circular stack, which I would think most of our sampling will be in circular stacks, we're dividing the stack surface area into equal sections of a pie, if you think about it. So you can see here that in this particular stack, we're sampling 12 locations, and each one of these particular areas, so this here, and this here are all equal surface areas. Now they're different shapes and different sizes, but the total surface area is exactly the same for each point. So basically we're taking that cross-section of the stack and cutting it into equal pieces. So now we know that we're sampling on all equal pieces all across the stack, so we can take a representative sample of the dust coming out. And you will notice that we never sample in the middle of the stack. We're always jumping across, because as we cut that piece of pie open, we're going to sample in the middle of each of those pieces. So theoretically, in this picture, this sample point would be closer to the middle here. And same with this one, and this one, and this one here. So that's what we're determining during method one. We're determining where on those points that we're going to sample, taking into account certain things like the width of the stack wall and the width of the porthole and things like that, to make sure that we're only looking at the inside diameter of the stack. And then on a square or rectangular stack, we're basically doing the same thing, just in a linear progression across the stack, cutting it into equal sections to be able to sample in the middle of each individual piece to get a representative sample. So this is how you would, in practical senses, mark the probe. So you've made your calculations, and you're going to measure from the very tip, so the very end of your nozzle, start marking your traverse point measurements back. And a little trick, do you know the ceramic whiteout that people used to put on paper when they made a mistake, the old days of a typewriter? That's a good little tool to use, because it's ceramic, so it won't come off in the heat, but it's easy to scratch off and make it disappear for your next job. So most stack testers in the US have the little white bottle of the whiteout, it's called. I'm not sure another term for it. But you can use that to mark your markings across your probe, so as you coming out, it's a reference point for you, and you know where to stop when you're sampling each one of these points. So as a point of reference too, we always start all the way in the stack and come out as we traverse, okay? So this would be our point one, and you can see here, as the stack tester, you would have had the probe marked right here, so you'll see that on your port, and then as you pull out the probe, when you see your marking for point two, you stop. You adjust your isokinetic sampling rate, because there will be a change in flow. Maybe it's very small, maybe it's very big. But what we'll do is we'll wait for our delta P, which is our flow rate from our pitot, to stabilize. So as we move, it's going to bounce and then come nice and steady. And then we'll times that by our K factor. And now we know how to adjust our console for our delta H number to get back to our isokinetic sampling. So we must be looking at this every time we move the probe. We need to adjust our flow rate, okay? I've been to many countries where they don't do this. I'm not going to name any names, but they make an assumption, or they make an average. But the problem is, now on the average, you might be close to 100% isokinetic. But maybe here, you're up 50%, and here, you're down 50%. And we know from those previous slides, now we're sucking in more big particulate here, or we're pushing the particulate around the nozzle on this particular point. So we're not really getting a sample of what's actually in the stack, which is important. So you would traverse across all the way, all points, stop here. Then we're going to turn off our pump. Not turn off, shut the valve. Leave it running, but shut the valve. As we pull our pitot out, we don't want to draw any ambient air in our nozzle and in the gas meter. Because now we're pulling somewhat clean air, cleaner than the stack, air through our system as the probe is out and we're moving around to the side. So now we're biasing our results where the gas meter would still be counting gas, but the gas is ambient air, which is cleaner. So we're going to lower our emission rate results. So always turn off the pump, leave the pump running, but turn off the valve, move it around the other side, then open it and start again. This is very important. Again, a little trick. So, and then you would do the same on port B or the second port. In the ideal situation, you would have access to 4 ports. So you would sample 3, 3, 3, 3. Does this ever happen in Thailand? Not very often. Do you at least get 2 ports? Always? 90%? Sometimes 1? Yeah. And again, this is something that's out of our control, right? I mean, we can ask our customer, is it possible to add a second port at 90-degree right angle, then we could do our job correctly. If you only get 1 port, you do the best you can. You sample your 8 or your 12 points and the 1, but make sure you note in your report that I was only given access to 1 sample line. Because again, now how do we know that if we have cyclonic flow and we're sampling directly across the stack here, 80% of the flow might be on this side here. It might be bouncing off the wall and coming back around. So maybe 80% of the particulate, the dust is coming up this side of the stack, but we've just sampled straight across the middle. The emission rate's going to look great. It's going to be pretty low, but maybe it's not a true representation of what's actually coming out at the top. So these are some of the challenges that we face every day, being in the field and doing what we can. But it's very important to note this down and make sure that you made variations or changes to the method. It wasn't exactly as it's written in the book. So method 2, we're determining our velocity. So without our nozzle on, we won't have our nozzle, but we're going to use our S-type pitot to traverse across the stack, take our flow readings from our delta P number on the console, and get an average flow rate across the stack. Again, what this is going to do is going to help us determine the best nozzle size to use so we can draw that vacuum through the system and get to isokinetic sampling as close as we can. So you'll see here that this is exactly the same as what we have here over on the end of our probe, but this is our S-type pitot here. This is our impact side, our negative side. It gives us a differential pressure and then gives us a reading of how fast that gas is coming up. So again, this will be missing on our, because we haven't determined the best nozzle size yet. So you can have no liner, no nozzle. And it's important to have no liner and no nozzle because you don't want to start collecting dust in that already because you haven't started counting the amount of gas that you're sampling. So even if you install your liner inside the probe and you do your method 2 velocity traverse, you're going to start getting dust inside that liner. Now you're biasing your results high because now you've started collecting dust that you're not accounting for in the gas flow. So no liner, no nozzle, do your traverse, do your calculations for your method 2, your flow rate, and then we'll use that in our K-factor calculation. And again, this is our equation that we're going to use for our method 2. Again, I'm not going to go into huge detail, but things we take into account is temperature, pressure. We will use our molecular weight number, static pressure, barometric, things like this. Method 3 is determining our dry molecular weight of the gas. How heavy is it? Basically, the composition of the gas. Now, in some countries, you can use a flue gas analyzer to do this. Is this okay in Thailand? Okay, perfect. In the US, this is not acceptable. I guess the question of PID technology, the little sensors, the little small sensors in the flue gas analyzers are not yet approved for reporting in the US. You can use it for process monitoring. If you want to check CO or CO2 at the exit of your boiler, this is perfectly fine. But for reporting to the government, you must use an approved method from the EPA, which is either an ORSAT device like this or FireRite, which is a small device like this to determine our molecular weight. So you guys have a distinct advantage here in Thailand to use a flue gas analyzer. It is acceptable in Europe as well and many other countries. Honestly, I just think the EPA is a little slow in picking up new technology. I think that's partly determined due to the budget at the US EPA right now. In some instances, they have a 5 or 10 year backlog of things that they should be doing. So I don't think it's a reflection on the technology. I think it's just the time needed to get it approved. So again, you're going to use your flue gas analyzer to get your gas values, which is going to help determine our molecular weight, again used in our K-factor calculation. And then our method 4 is our determining the moisture. There's several ways we can do this. We can do it gravimetrically, so we can actually collect water in our impinger bottles in the glassware in the back, and then we can put it on a scale and measure how much water we've collected. We can do what's called a wet bulb, dry bulb technique, where we put a thermometer in the stack with a dry piece of material over it. Then we put it in with a wet piece of material over it. And we have a scale that we can determine how much moisture in the stack based on the variations of those two readings. And then in the US as well, if we have a moisture analyzer installed on the stack, like a moisture SEMS unit, we can use that value if the plant operation will give that to us. Even many of my colleagues who've done this for many years can sometimes look at the stack and guess how much moisture is in there within a couple of percent, just from experience. And again, this is our moisture calculation for our method 4 that we're going to use again for inputs into our K-factor. And then we finally get to our method 5. And our method 5 is where we're going to draw our particulate matter. from the source and collect it on our filter, which is in our heated sample box, which we maintain at a constant temperature. So, which is 121 above the dew point, okay, keeping the moisture in the gas, plus or minus 14% Celsius. So obviously on our method 5, we've prepared the filter in the laboratory before we leave, okay? Again, I've been to some countries where they go up on the stack and they take a box of filters and they pull it out with their bare hands and they put it in the filter and they've already contaminated the filter. They've already added weight to that filter from their hands, from the ambient air, by not handling the sample correctly. So again, it's very important to weigh the filter in the laboratory, put it in the glassware, and seal it off on both ends. So it's completely sealed from the environment. Once you get to the stack, then you can install it and start pulling the gas through that material straight away. So this is important. Again, it sounds very simple when you talk about it. It makes perfect sense, but the practical application of doing this sometimes is not so strong. And once you explain it, people think, oh yeah, okay, now that I understand it, but they've never really thought through the process of why we do certain things to make sure we ensure we have a really, really good, accurate sample as best we can. So then what we'll do is we'll collect our dust from our method 5 run on our filter. We'll take it back to our laboratory. We'll put it in some kind of desiccation unit, withdraw the moisture out of the filter and the dust that we've collected. We get a post weight on our filter. So we know the weight we started, the weight we finished. We can determine how much dust we collected on our filter. Now we can do a calculation knowing the flow rate of our stack to determine how much total dust, how much total particulate is coming from that particular source. We can do a basic method 5, total PM dust, in combination with other methods like 23, 26A, 29 for metals, and 202, which is condensables. And this may be something that might be coming up here in Thailand in the future. It's a very, very hot topic right now in China, is this method 202. There's questions now that the condensable particulate, so when it's hot and in the gas, it acts or it looks like a gas. It may be invisible, but it acts like a gas. Once it enters into the atmosphere and the ambient air, it now condenses and turns into a solid. And that solid now is what China's looking at, is that contributing to their pollution problem. That a typical method 5 will not find this because it passes through the filter and into the impingers. So you're not collecting it. So there is a method, 202, that you have 2 filters. You collect the total PM in the front, then you cool the sample like it would if it was in the ambient air, and you collect now the new solid material that's now changed from a gas to a solid on the second filter to determine the condensable particulates that are coming out of that. So this is big in the US, big in China. Maybe it's something that might be coming here to Thailand as well, as the general population get more educated and ask the questions, you know, where is this PM2 coming from? You're telling me that every stack in Thailand has a low PM number. Where is it coming from? Maybe it's condensable particulate. We don't know. So just some requirements from method 5. Typically 60 to 120 minutes for one run. In the US, you must do 3 complete runs, 3 brand new filters, 3 complete sampling trains. Is this the practice here in Thailand? You do 3 or just 1? If you don't want to own up to me, that's fine. But in the US, it's 3 complete ones. So we can take all 3 values and plot them on a graph to make sure they're all close together. Maybe we have 2 here and an outlier. So we can determine maybe the high or low value of one of those runs is either incorrect sampling method, maybe the guy operating the box fell asleep or something like that, or maybe the process changed. Maybe the facility itself changed something during the sampling run which changed our sample value. So that's why we always, at least in the US, do 3 runs to make sure, okay, if they're all bunched together and they're all pretty close, I think we've got a good number. We did a good job. So let's talk about the 502 now. So how many of you guys know our manual sampling kit, the 572? You've seen it before. It's kind of our original product for isokinetic sampling. It's got the big 10-inch incline manometer on the front for our delta H and our delta P values. It's got an external pump. It's quite a big unit. So as we went into new countries, new regions, there were a lot of challenges in some parts of the world for getting access to the sample location on the stack. We're very fortunate in the US that most facilities either have an elevator that takes you to the top where you need to sample, nice big platform. Sometimes they're even inside the annulus, so if it's snowing outside, that you're nice and safe contained within the annulus. But after visiting many locations in China and India and places like this, the facilities, at least for our part of our job, is not that great. So we tried to develop some new technology to shrink the size of the unit, to make it lighter, easier for you guys to take it on site, get up there, but still keep the accuracy. So you can see here, this is our original box here, and you would also need the pump to go with it. So you're looking at 2 pieces of equipment together. You can see the 502, which you guys can see there in the back, is about half the size and half the weight. Okay, it's got an internal pump. Also has a lot of features that the manual system doesn't do. Data acquisition. It's always recording the information for you that can be exported later and used for your building your reports. So it cuts down on human error, maybe writing down manually numbers, reading. A lot of people don't realize that even small variations, so even reading the liquid in this manometer, if you read it from here or from here, it's going to give you 2 different values. You must read it straight on. So even those small little things in the manual system can change the numbers, right? And start adding errors into our calculations. Whereas our 502, it's all digitally displayed. The accuracy is much, much tighter and much, much better than our manual systems. So you can see here, this would be the start, and I'm sure we can show anyone who wants to get a closer look at the instrument during the break. But we're going to have our timer, our delta P, which is our reading from our pitot, and our orifice delta H that's coming off the back of our gas meter. Again, you can see here that this is displaying in inches. We can change that to millimeters. We can even change it to pascals in the software. It's all available. So metric units is no problem. And then our gas meter reading here. So another advantage too is we can see all of our temperatures, all of our thermocouples instantly on one screen. Previously on the older model, you would have to select which one you want to read and would only display one value at a time using the switch. Now we can take a quick look at that screen by pressing one button and see all of our thermocouple temperatures on one screen. So obviously the software is continuing to record all this information, but as a tester, you can quickly take a look and see if there's any problems. Quickly take a look and for some reason my oven temperature is only reading 100 degrees Celsius, okay? Where it should be 121 plus or minus 14, where outside of the method, maybe we need to stop and investigate, see what's going on. Is there a problem with the equipment, or is it exposed to some kind of cold ambient temperature? What's going on? So it allows us to get a quick snapshot there to see what's happening. Our vacuum, what time were we meant to? 10:30, okay. The next screen will show our vacuum, barometric pressure, time, and our run, and our point. And again, all this would be entered once you've done your isokinetic calculations. So the system itself will know that we're on our first run of 3, hopefully, and we're on our first point, or our second point, or our third point. And again, it will record all of this information for you and export it. Some of the features in kind of a sub-menu underneath our main screens. This is really for more servicing and operation. We can zero the pressure transducers. So in the console, we're taking the pressure reading by these little microchips in the back, these little computer chips. Due to various things, whether it be barometric pressure, humidity, temperature, they naturally drift a little bit. So you might take, in a nice air-conditioned room like this, it's reading 0. By the time you travel 3 or 4 hours,